Okay, so let us continue with exercise 76. So here we are given a group G, a subgroup H of G, and for any element small g in G, we are defining a subset like this, GH, whose elements look like this, where G of course is this fixed G and this small h is varying over capital H. Now, if our group G is abelian and this element small g has order 2, we have to prove that this union of H and that subset GH is a subgroup of G. So that is the first part of this exercise. We are coming to that second part later. Okay, so let us start with the solution. We need to prove that K is a subgroup. So we start with this observation. Clearly, K is non-empty because K is a union where one of the sets in that union itself is a subgroup. So that is non-empty. So that's why K is also non-empty. Let X and Y be two elements in K. Now since K is a union, each of these elements belongs to either H or GH. So accordingly some cases arise. So we are now going to look at each case separately. If it happens that X and Y are both in H, then definitely XY inverse is also in H, since H is a subgroup. And hence XY inverse belongs to K because H is contained in K. The next case is this: if X and Y both belong to GH, so that X is equal to say GH1 and Y is equal to GH2, for some elements H1 and H2 in H, then XY inverse is equal to GH1 GH2 inverse. Now we know that in a group, inverse of GH2 is H2 inverse G inverse. Okay, now because we are in an abelian group, so this becomes equal to G inverse H1 H2 inverse. In place of H1 H2 inverse G inverse, we can write G inverse H1 H2 inverse. So this gives us H1 H2 inverse, which is again in H, because H1 and H2 are in H and capital H is a subgroup. Note that we have used the fact that G is abelian. Okay. Now two more cases are left. One of them is the one where x belongs to h and y belongs to gh, and the other is where y belongs to h and x belongs to gh, but they are similar, so it's enough if we deal with only one of them. So next, let x belong to h and y belong to gh. Since y belongs to gh, it is of a particular form, so that's why let y equal to say gh prime, where h prime belongs to h. Now again, in this case also we are going to calculate xy inverse. Then xy inverse becomes x gh prime inverse, that is equal to x g inverse h prime. No, it won't be in this order, it will be in the reverse order. H prime inverse G inverse. Okay, now we are going to use the hypothesis that G has order 2. Since G has order 2, we have G square equal to identity or G equal to G inverse. Okay, hence xy inverse, which is x won't have that much space here, x h prime inverse G inverse, this becomes x h prime inverse G. But again we can use the fact that G is abelian, and this time we are not going to mention that, we will just simply write in place of this. Okay, and this particular thing, this element belongs to GH, since x h prime inverse belongs to H. How are we having this? We are having this because in this case, in this third case, x belongs to H, H prime also belongs to H. So this product, this element also belongs to H, since H is a subgroup. Hence, xy inverse belongs to K, because GH is also contained in K. K is the union of H and GH. The case where x, this is the only other case left, x belongs to GH and y belongs to H, also leads to this same conclusion. Although the conclusion will be reached in slightly different manner, I mean will be actually different strictly speaking, but it will be similar to this one, the third case. So in any case we have xy inverse belongs to K. Thus K is a subgroup of G. Okay, so that is the first part of the exercise. In the second part, this is the second part. Is your proof valid if we drop the assumption that G is abelian? G is no longer an abelian group, not necessarily an abelian group. It may or may not be abelian, we don't know. And in place of an arbitrary subgroup H, we are considering the center of the group G and forming another such set K, similar to how we formed the previous one. Then is this conclusion still true? That is this K still a subgroup of G? We are now going to show that it is. So that is the second part. Okay, next let G be any group not necessarily abelian. G may be abelian, we don't know and we won't be able to use that fact because G may as well be non-abelian. Let small g be an element in G and let this have order 2, and finally let K be the union of the center of G and this other set formed from the center and the element small g. Okay. Now our aim is to again show that K is a subgroup of G, so we will proceed similarly. Again, clearly K is non-empty because of that same reason, that the center being a subgroup of G is non-empty, so K is also non-empty. Now let say alpha and beta be two elements in K. The pattern will be exactly the same that we have here in the first part. If alpha and beta belong to the center, then alpha beta inverse also belongs to the center because the center is a subgroup. This time we are not going to write all those things, and hence alpha beta inverse belongs to K. Okay. If alpha and beta belong to G times center, so that alpha B, say GZ1 and beta is GZ2, for some elements Z1 and Z2 belonging to the center, then alpha beta inverse will be equal to GZ1 times GZ2 whole inverse, so this is Z2 inverse G inverse. Okay. Now we stop the argument, I mean these equations we stop here. Now note that since Z1 and Z2 are central elements and the center is a subgroup, so Z1, Z2 inverse itself is a central element. In the previous part, at this stage, I mean there also we had a stage like this, we used the fact that the group is abelian to bring G and G inverse together, which then vanished. This time we cannot do that because we don't know whether the group is abelian or not. In fact, it may be non-abelian. So instead we are going to use the nature of Z1, Z2 inverse as a central element to do that same thing. So we write here, since Z1 and Z2 belong to the center, we have this also belonging to the center, and hence this commutes with every element of G. In particular, it commutes with G inverse. Thus, alpha beta inverse, which is this, is equal to this implies alpha beta inverse belongs to K. Okay, so here also, just like before, we are going to have a third case. Next, let alpha be a central element and beta be an element in this. Let beta be equal to alpha z prime for some z prime in the center. Again, we are going to calculate alpha beta inverse. Then now what have I written here? Oh, sorry, G times. Sorry about that. Alpha beta inverse is alpha G z prime inverse, so that becomes alpha z prime inverse G inverse. That is equal to G inverse alpha z prime inverse. That is equal to, let us just write the steps and then we will justify each one of them. G alpha z prime inverse, and this belongs to this, since alpha z prime inverse is itself a central element. Why? Let us see why this is true. first of all, alpha is a central element, Z prime is also a central element. So alpha Z prime inverse will also belong to the center. Now what will happen because of this? In this step, because this is a central element, it commutes with G inverse. So we have been able to bring G inverse to the left of this element. And then again, this condition that G has order 2 still continues to be true. It's still a hypothesis in this second part. So because G has order 2, so G inverse will be equal to G just like before. And again, because this belongs to ZG, so by the definition of this subset, this element will belong to GZG. Hence, alpha beta inverse belongs to K, and just like before, the case where alpha belongs to GZG and beta belongs to the center also leads to that same conclusion. So in any case, we have alpha beta inverse in K. Thus again, this new K is also a subgroup of G. The proof structure of this second part is the same as the first one. However, some reasons or some justifications are different because K is different and G is also not necessarily abelian. Anyway, so this is the solution. Here it ends. Then next, exercise 77. Let A belong to a group and let it have order m, some positive integer. If n is relatively prime to m, okay, n is some integer that is co-prime to m, show that the element A can be written as the nth power of some element in the group. So in the very beginning, right off the bat, we are going to use this hypothesis that n and m are relatively prime. Since GCD of n and m is 1, we have say alpha n plus beta m equal to 1 for some integers alpha and beta, because the GCD of two integers when it exists is a linear combination of the integers with integer coefficients. For some integers alpha and beta. Okay, now our aim is to express a as an nth power. So we start with a. Now a is equal to this integral power a to the power 1 of a. Now in place of 1 we are now going to write this expression, which involves integers a to the power alpha n plus beta m. In the next step we use the rules of exponents that are true in any group, and we write this power as a to the power alpha whole to the power n times a to the power m to the power beta. Now we use the hypothesis that the order of a is m, so a to the power m will be identity, so this will be equal to times identity to the power beta. Any integral power of the identity element is the identity element. This can be proved easily by first of all induction on the exponent when the exponent is non-negative, and then using that we can prove the case when the exponent is negative. This is always going to be E. So that's what we wanted. We wanted to show that a can be written as the nth power of some element in the group, and that some element in this case is a to the power alpha. So here the solution ends. Then there is one involving the dihedral group. I have it here, 78. Let F be a reflection in the dihedral group Dn and are a rotation in Dn. Determine the centralizer of F when n is odd. Also, the centralizer of F when n is even. And lastly, we have to determine the centralizer of the rotation R. So we first recall a fact about dihedral groups, that the rotations are, all the rotations in a dihedral group are actually generated by a single rotation, and that rotation is this. R360 divided by n. That is the rotation through the smallest possible angle. That also is a symmetry of the n-sided polygon, a regular polygon, and that belongs to the dihedral group Dn. All the other rotations are powers of this. Okay, so that fact we are first going to recall, and that will tell us something about this particular exercise. We know that the rotations in Dn, rotations means all the rotations in Dn, form the cyclic subgroup What does this mean? It means, of course we know what it means, but it implies for this particular exercise that any two rotations commute with each other. Okay, so that means if we have, for example, this particular rotation, whatever it is, it has been considered here. Let R be a rotation in Dn. Every other rotation will commute with this rotation. So all the other rotations will belong to CR, C of R. Hence, every rotation in Dn commutes with every, okay, it sounds slightly bad, any two rotations in Dn commute. Hence, any two rotations in Dn commute with each other. And hence this cyclic subgroup consisting of all the rotations is contained in the centralizer of R. Now we also know the fact about Dn that every element in Dn is either a rotation or a reflection. So all the rotations have already come inside the centralizer of R. Now we have to decide whether any reflection also belongs to C of R. Okay, so for that we are now going to see which, so we know that rotations commute with one another. We will now have to see when a rotation commutes with a reflection and when two reflections commute. These are the two things we are now going to see. So this we will do in general for an arbitrary rotation and an arbitrary reflection, because the C and R the F and R we have here, they are fixed, they have already been chosen in Dn. Okay, so in the next paragraph we consider this. Let F prime be any reflection in Dn and R prime be any rotation in Dn. First we see this. Since F prime R prime, what will this be? Since this is an orientation changing transformation, this cannot be a rotation, it will be a reflection. We have already seen these things before. Since this is a reflection, we have F prime R prime, F prime R prime, which is F prime R prime square. So all when we take the square of a reflection, we get the identity element R naught, which implies F prime R prime F prime is equal to R prime inverse. So that means for any reflection F prime and any rotation R prime, this is a general identity that is true in Dn. Okay, now we see what happens if F prime and R prime actually commute with each other. Now assume that F prime and R prime commute. That is, F prime R prime is equal to R prime F prime. Then if we invoke this new condition here, what do we get? Do we get anything new? R prime, which can be written as R prime R naught, because R naught is the identity, and in place of R naught we can write F prime square. Because F prime is a reflection, so its square will be the identity. So this is equal to R prime F prime square, which itself can be written as this. Okay, so far we have not used this, but now we are going to use this. In place of R prime F prime, we are now going to write F prime R prime. And you see that it is nothing but this, so which is equal to R prime inverse. Okay, thus R prime, we started with R prime and we ended with R prime inverse, or R prime square equal to identity. Identity in Dn is R naught, If you want, you can write E also, it does not matter. Okay, so what have we got now? If the reflection F prime and the rotation R prime commute with each other, then R prime must be a rotation such that its square is the identity. Okay, so this is one thing we are getting, and in fact, depending on what the parity of n is, that is whether n is even or odd, we can decide what R prime actually will be. In fact, let us just write that. So R prime is equal to R naught if n is odd. If n is odd, there is only one rotation whose square is the identity, that is the identity itself, R naught. And R prime is equal to R naught or R prime is equal to R 180 if n is even. If n is even, then besides R naught, there is R 180 also in Dn, whose square is also the identity, because 180 is half revolution. If you perform it twice, then that is the same as performing doing nothing. Okay, so that is R naught. So these are two cases. Now we are going to see what happens when two reflections commute. Okay. Now we can take two different reflections also. Different means in the sense that not this F prime, because we have used F prime here. If you want, you can still use F prime and maybe another reflection, but we want to start afresh. Okay, so let F1 and F2 be two reflections in in Dn. Then F1 can be written as F1 R naught. In place of R naught, we can write F2 square, because F2 is a reflection, so its square is identity. So that is equal to F1 F2 F2. Okay, and that is equal to, say, rho times F2, where rho is F1 F2. So we have expressed F1, the reflection F1, in terms of the reflection F2, where this another element rho has appeared. Note that rho is a product of two reflections, so rho is itself a rotation. We have seen this thing before. You perform F1 and then on the polygon, inside a regular polygon, you again perform F2. So F1 F2 does not change orientation, so it's a rotation. Note that rho is a rotation. Okay, now if we assume that F1 and F2 commute, then what happens? Okay, we are going on writing now. Okay, fine, we can write now. f1 and f2 commute, that is f1 f2 is equal to f2 f1. Fine. Now from this we will get a condition on this row, and that condition will be this. How did the calculation start here? If we started with f1 f2, okay, let us start with f1 f2. Now we have f1 f2 equal to but f1 f2 is already we are denoting it by row. So what we want is to calculate row inverse. Okay, fine. So let us start with row inverse. So this is f1 f2 whole inverse, that is f2 inverse f1 inverse. Okay. Now since f1 and f2 are both reflections, so the squares of both of them are equal to the identity, and hence both of them are equal to their own inverses. So f2 inverse is f2 and f1 inverse is f1. Okay, but that is f2 f1. Now because of our assumption f2 f1 is equal to f1 f2, this is equal to f1 f2, and that is nothing but row. Which implies again row square is equal to identity means R naught. So same conclusion like this one. Hence row is equal to R naught if n is odd and row equal to R naught, or row is equal to R180 if n is even. Okay, so now we know which rotations commute with each other. In fact, any two rotations commute with each other. Which rotations commute with which reflection, and which two reflections commute with each other. All these things we now know. So now we should be able to determine the centralizers exactly. Thus taking into account all of the facts in the paragraphs above, we have, first of all, we write the centralizer of R. Okay, so we were saying that we already observed that the centralizer of R contains all the rotations. Does it contain reflections also? Note that if a reflection commutes with a rotation, then the rotation is either equal to R naught if n is odd, or equal to R naught or R180 if n is even. So that means if this R is equal to R naught, then obviously any reflection commutes with that R, that is R naught, which is anyway it is true because R naught is the identity, so everything commutes with the identity. So this is equal to the entire Dn if R is equal to R naught, and this does not even depend on whether n is even or odd. But if n is odd and R is not equal to R naught, then the centralizer of R does not contain any reflection, because in that case no reflection commutes with R. Do you get the point? If our R is different from R naught and if n is odd, then clearly, since this is the condition, this is the only condition in which R will commute with some reflection. So if this condition is not satisfied, then no reflection commutes with R. In other words, the centralizer of R consists of only the rotations. So in that case, the centralizer is the subgroup of all the rotations, this cyclic subgroup. If R is not equal to R naught and n is odd, so that is another condition. Then we come to the case when when n is even. We have already seen what happens when R is equal to R naught, so we need not say anything about it once more. Now, if R is equal to R180, then again any reflection commutes with that particular R. Okay. And so in that case again the centralizer of R is Dn. So this is equal to Dn if n is even and R is equal to R180. It's better to say n is even first before writing R equal to R180, because when n is not even, R180 is not an element of Dn. Okay, only regular polygons having an even number of sides have this symmetry, R180. Triangle does not have this symmetry. Pentagons don't have this symmetry like that. Squares, hexagons have this symmetry. And finally, if n is even but R is not equal to, R is neither R180 nor R naught, that we have to mention here in this specific case, then again CR is equal to this. So this is equal to if n is even and R does not belong to this set, R not R 180. So this is the centralizer of R in all the possible cases. Like that, we are now going to write the centralizer of F. But before we, let me write, you will understand. And what about the centralizer of F? For this, the centralizer of F is this two element subgroup if n is odd. Okay, what did we do there? You see, we considered to but here again we have to take into account that thing, that which rotations belong to the centralizer of F, where F is a reflection. If n is odd, then the only rotation that commutes with F, we have already seen here, is R naught. Okay, so that thing is there. So that rotation has come inside the centralizer of F. So rotations, we have dealt with rotations. No other rotation will come inside the centralizer. Now what about the reflections? Say F commutes with F prime. Think of F as F1 and F prime as F2. Then we can, in fact we have there expressed F as rho times F prime, but of course we can express F prime also as rho times F, where in place of rho you have to write rho inverse, which itself is also a rotation. Okay, so F prime is equal to rho F. Then we again found conditions like this. So if n is odd, then the only possibility for rho is R naught. So if n is odd, correspondingly the only possibility for F prime is R naught F, which is equal to F. That is, the only reflection that commutes with F when n is odd is F itself. No other reflection commutes with F. That's what we are getting from this analysis. So that's why we have written R naught comma F. R naught is the only rotation that commutes with F, and F is itself the only reflection that commutes with F. So in this case, this is the centralizer of F. Now what about the case when n is even? There, when n is even, so again the question of which rotations commute with F, that question again comes, which we have already seen. When n is even, there are two rotations that commute with, precisely two rotations that commute with F, R naught and R 180. So they will belong to the centralizer of F. So let's write them. And what reflections commute with F? They will be determined by the possibilities for rho. Say F prime is the reflection that commutes with F, then when n is even, row has two possibilities, R0 and R180. So accordingly there will be two f primes. One of them is of course this, which is coming because from R0, and the other comes from this. Okay, that is a new reflection. So here we have two reflections. One of course is f itself, and the other is R180f if n is even. So these are the possibilities for the centralizer of f. That's it. That is the solution. It may seem somewhat confusing at first, but once you go through the solution once or two times or three times, then things will become much more clear. Okay, so next again we have to find centralizers, but this time in general linear group. Exercise 79. Let G be the general linear group of 2 by 2 real matrices. So we know that the elements here are 2 by 2 real matrices which are non-singular, which have non-zero determinants, and the binary operation of course is matrix multiplication, and there are three parts. Find the centralizer of this particular matrix 1 1 0 1 row wise. Okay, row wise. The 1 1 is the first row, 0 1 is the second row. Part B. Find the centralizer of this matrix 0 1 1 0. And part C. Find the center of G. Okay. Excuse me. Okay, so let's see the solution. A. At least in this case, the calculation is, I won't say it's easier than this one, but it is, we are more familiar with this type of calculations. Let the matrix A, B, C, D belong to the centralizer of this given matrix. That means ABCD will commute with this matrix. We will now find a necessary and sufficient condition on these elements A, B, C and D, these entries, so that the matrices commute. Then let's do the calculation here. ABCD 1 1 0 1 this is equivalent to A plus 0 A plus B, C plus 0 C, C plus D. A plus C, B plus D, 0 plus C, 0 plus D. If and only if A is equal to A plus C comma a plus b is equal to b plus d. C of course is equal to c, and c plus d is equal to d. So we can simplify things. C is equal to 0, b is equal to d, and again from here we are getting c is equal to 0. So the centralizer of this matrix 1 1 0 1 consists of matrices of this form. C has to be 0, so that means this will be 0. B has to be equal to D, okay, and no, sorry, I think I am what? B is not equal to A is equal to D. Sorry about this. I hope I have done it correctly. Let me just see once more. ABCD 1101 1101 ABCD, A plus 0 A plus B, C plus 0 C plus D, okay, A plus C, B plus D, 0 plus C, 0 plus D. So A is equal to A plus C, A plus B is equal to B plus D, C and C are the same, C plus D is equal to D. So from here we have C equal to 0, from here we have A equal to D, okay, and again we are getting C equal to 0, fine. So C is 0, A and B are the same, sorry, A and D are the same, and what about B? This doesn't say anything about B, no? This doesn't say anything about B. Somehow I made up, because it's not matching with what we have here. A plus C, B plus D, have I considered the matrix proper? Oh no, I think I have taken down the wrong question. Oh, sorry about this. This is 1 0. Yeah, how will it have the same answer? Okay, so now everything will change. A plus B, A plus B, A plus 0 is A, C plus D, C plus 0 is C, A plus C, B plus D, fine, and here we will have A and B, okay. So A plus B is equal to A plus C, A is equal to B plus D, okay, C plus D is equal to A and C is equal to B. Entirely different conditions. So B is equal to C, that's what we get from here. A is equal to B plus D, okay, that is still there. C plus D is equal to A, but if we use the fact that B is equal to C, then we get A is equal to B plus C. Okay, let us just write the condition as it is, and this we already have. So now what can we write? B is equal to C, so that means we can write like this. Okay, if we keep A as it is, then D is A minus C, but since B is equal to C, so we have A minus B, where A and B are real numbers, and we want non-singularity also, so that determinant should be not equal to 0. What is the determinant? A square minus AB minus B square. This. You don't have to mention this if you mention that this matrix belongs to our G, because then automatically it means that the determinant has to be equal to a non-zero real number. But anyway, the answer is given in this fashion in the book itself, so we are also writing like this. Yeah, now it's okay. Have I taken the second one down correctly? Yes. Okay, so this is A, then B. Let again A, B, C, D belong to, now this time our matrix is this. Then A, B, C, D zero, 1, 1, 0, A, B, C, D, 0 plus B, B, A plus 0, A, 0 plus D, D, C plus 0, C. So it interchanges the two columns. This becomes the second column, this becomes the first column. I think here the rows will be interchanged. 0 plus C, C, 0 plus D, D, A plus 0, A, B plus, yes. See, the first row has become the second row and the second row has become the first row. So if and only if, and that is because this is an elementary matrix. When we multiply by an elementary matrix, a given matrix either from the left side or the right side, then elementary row operations are performed or elementary column operations are performed. If you multiply from the right side by an elementary matrix, then the columns change accordingly, and the rows change if we multiply from the left side. We will discuss about these things when we learn about matrices separately. So here the conditions are these: B is equal to C, A must be equal to D, and again from the second row also we will get the same conditions. Hence the centralizer of this matrix consists of matrices that look like this. D is also the same as A and this, where A and B are real numbers and A square minus B square is not equal to 0 to have non-singularity. And lastly, in part C, we have to find the center. Let R be any real number. Note that for any matrix A, B, C, D in G, we have, I need ink. We have A, B, C, D, R0, 0, R. Say we calculate this product, what do we get? AR plus 0, so we get AR, A0 plus BR, okay, CR plus 0, C times 0 plus D times R. So that means all the entries are being multiplied with R. And what happens if we change the order and calculate the product? RA plus 0, RB plus 0, 0 plus RC, 0 plus RD. So that means this matrix commutes with any matrix in G. This implies this belongs to the center of G. Okay. Now let alpha, beta, gamma, delta belong to the center of G. Then what should these entries be, alpha, beta, gamma and delta? Let us see. This belongs to the center means it commutes with every matrix in G. In particular, it commutes with this matrix and also that other matrix 1 1 1 0. Then this commutes with let us first consider the first matrix 1 1 1 0, and hence we have already found the general structure of the matrices that commute with this one, and according to that structure, so the matrices that commute with this one look like this. A minus B. Of course, keeping in mind that it has to be non-singular, that thing is there, but this matrix should be like this. That means beta should be equal to gamma, and what about the relationship between alpha and delta? Or delta should be equal to A minus B. So delta should be equal to alpha minus beta. So we first write that, and hence beta equal to gamma and delta is equal to alpha minus beta. So we must have our matrix like this: alpha, beta, beta, alpha minus beta. But again, the matrix should also commute with that other matrix, since this matrix also commutes with 0 1 1 0. We further have, we will further have what? Now for this type of matrices, the structure is this. That is, this entry should be equal to this entry, and this entry should be equal to this entry. These two are already equal, so these two should be equal. We further have alpha equal to alpha minus beta, which implies beta is equal to 0. Hence, what is the final form of our matrix? Since beta is equal to 0, so the matrix looks like this. So you see that if this is a central element, a matrix in the center, then it is a matrix of this form. Conversely, every matrix of this form belongs to the center. So these are precisely the matrices that form the center. Hence, or thus, the center of G, general linear group, consists of matrices of this form, where R is a real number, and to maintain non-singularity, we require that R be non-zero. This type of matrices have a name. They are called scalar matrices. They can be obtained from the identity matrix by multiplying the identity elements by a single real number. Okay, so here the solution ends, and there is only one more exercise left in this set of exercises. And that is number 80. let G be a finite group with more than one element. Show that G has an element of prime order. G has an element of prime order. Okay. Let A be an element, since it's given that G has more than one element, so besides the identity element there is something else in G. Let us choose one such element. Let A be an element in G different from the identity element. Okay. Now consider the elements A square, A cube, etc. This is the list of all positive integral powers of A. These elements are all in G because G is closed under the product that is there in G. Since G is finite, the above list of elements must have repetitions. That is because all these elements cannot be distinct. If they are all distinct, then we are having infinitely many elements in G, which is not possible because it's given that G is finite, so they cannot be distinct. So two of these powers somewhere have to be equal. In fact, there will be many such repetitions, but there is at least one repetition. We need only one. So there exist positive integers I and j such that I is less than j and a to the power I is equal to a to the power j. You have got some a to the power I, and then that element has got repeated again as a to the power j. So although I and j are different, but the powers are the same. As integers I and j are different, but the integral powers a to the power I and a to the power j turn out to be the same. That is one repetition. Then using the rules of exponent or using the calculations we ordinarily do in a group, a to the power j minus I is equal to the identity. Since j minus I is a positive integer, a has finite order. Because one integral power of a has been found, which becomes the identity, and where the exponent is a positive integer. So the least such positive integer will be the order of a, so which has to be finite, and in fact it will be less than or equal to j minus I. So what we have proved here is that any non-identity element of G has finite order. Identity of course also has finite order, its order is 1, but non-identity elements also have finite order. Okay. And there are finitely many elements. So the set of all possible orders itself is finite, and in fact that is a subset of the set of all positive integers. So by the well ordering principle, it will have a least element. We have thus proved that every non-identity element in G has finite order. We are not going to write in that much detail that because of well ordering principle there is an element of smallest possible order. We are just simply going to mention that. We are simply going to use that. Let A be a non-identity element of G having least possible order. Okay, so there are orders which are positive integers. So some order will appear which has the minimum possible value in G. Okay. Now, since the identity element in G is the only element whose order is 1, we must have the order of this non-identity element greater than 1. So that means this order is a positive integer greater than 1. So whenever you have a positive integer greater than 1, question of the integer becoming prime or composite comes. Now our claim is that this is a prime number. Suppose to the contrary that it is composite. Suppose this is composite, then this is equal to, have we used any n or m? No, we don't have any n m here. So let this be equal to nm, where n and m are integers satisfying these inequalities. These are n and m are proper divisors of the order of A. It's like this: 6 equal to 2 times 3. Both 2 and 3 are greater than 1 as well as less than 6. This factorization of the order of A is like this and not like this. Okay. And because of the our supposition, compositeness of this means there will be one such factorization like this. Then what about a to the power n whole to the power m? What about this integral power? By the rules of exponent, we have this, which is equal to identity. Okay. So now you look at this equation. The mth power of the element a to the power n is identity. So the order of a to the power n is less than or equal to m, because m itself is a positive integer. So this is less than or equal to m, and m itself is, or let us just write that in another line. Since m is less than mn, which is equal to order of A, and this is the least possible order of any non-identity element in G, we must have a to the power n equal to e, because you see the order of a to the power n according to this equation has to be less than or equal to m, and since n is greater than 1 on both sides of this inequality, if you multiply by m, you get m less than mn. So m becomes less than the smallest possible order, and this equation is saying that the order of a to the power n has to be less than or equal to m. Now, smallest possible order of a non-identity element in G. So that means a to the power n cannot be a non-identity element. It has to be the identity element. But then according to this equation, the order of A should be less than or equal to n. Now you multiply on both sides of this inequality by n and you get, now this is an absurdity, order of A becoming strictly less than itself, which is not possible. So we have come to a dead end. There is nothing else we can do to salvage the situation except if we change the supposition, because that's where all the things are coming from. Hence, our supposition is wrong. That is, this must be prime. So that means you choose an element in G that is non-identity and that has the smallest possible order, then its order has to be prime. So that's how you get an element in G of prime order. So the solution ends here. And in fact, this set of exercises also ends here. After this, we will go to the next set of exercises, which is on cyclic groups, but that we will do in another video. So we end this one here itself. If you have any doubts regarding this or any other matter related to mathematics and other subjects which are related to mathematics, you can write in the comment section below, or you can mail me. You can find the mail address. Let me write it here. It's there in my Facebook page, but since that is not visited by many, or many people don't even know about that, so let me just write the mail here. So that will be all for today in Gallian's exercises. So see you next time, or see you in another video, not necessarily about these things, but about the other things that we are doing. So until then, it's me, Lucifer, from a mathematical room. Have a nice night.